The first library we'll take a look at is referred to as Spark SQL. It's named this because it works with your data in a similar fashion to SQL. In fact, there's been mention that its goal is to eventually meet SQL 92 standards. But the gist is that it allows the developers to write declarative code, letting the engine use as much of the data and storage structure as it can to optimize the resultant distributed query behind the scenes. The goal here is to allow the user to not have to worry about the distributed nature as much and focus on their business use case. A Databricks blog post puts it best, saying that as Spark continues to grow, we want to enable wider audiences beyond big data engineers to leverage the power of distributed processing. So, how does Spark SQL compare to its competitors? First, there's Hive, which is orders of magnitude slower and requires oft complex, custom user-defined functions simply to extend its functionality. And unit testing Hive? Well, that's a nightmare. As to parity, there are some differences between Hive and Spark SQL, but much of that is easily worked around with easy extensibility. But if you already have an existing Hive database, don't fret. There are mechanisms in Spark to take advantage of existing Hive table structures, even running 10 to 100 times faster than pure Hive. And we'll cover its integration shortly. Next is Apache Drill, which focuses on more than just SQL on Hadoop. It's ANSI SQL 2003 compliant, extending beyond for a more powerful basic SQL engine. However, Spark SQL is better for more complex querying and analysis. Impala, on the other hand, is an established C++ tool which tends to beat Spark in direct performance benchmarks. It was built from scratch for more specific cases than Spark's general engine, so is especially optimized for this task. But if you combine Spark SQL with machine learning, streaming, or any of the other utilities built right into Spark, then not needing to switch programming or even data flows often makes Spark the better choice overall. And another benefit is Spark's ability to work with different data sources, a number of which are built right in. One that we've already mentioned is Hive. In fact, Spark SQL originated out of a product named Shark. Shark was pretty much Hive on Spark and was quite successful. However, this meant that it was coupled to Hive, so it was rewritten in favor of decoupling the code while keeping the best parts, becoming Spark SQL. But if you do want to couple with Hive, then you'll need to copy your Hive site.xml file into your Spark Homes conf directory. After that's done, you'll automatically have access to your Hive metastore. If you want to access an existing table, just load it by name. It's as simple as that. In fact, Hive on Spark is nearly at parity with Hive functionality, even supporting your SERDES and UDFs. And there are other natively supported data sources outside of Hive, such as JSON, CSV, and Parquet. But if not native, it's fairly simple to pull in an external library via Spark packages and gain support for Avro, Redshift, and a number of other data sources. In fact, Spark SQL is generally suggested as the starting point for most applications. Why? The optimizations that it can bring, like predicate pushdown and column pruning, for example. Predicate pushdown is where the optimization engine can look at your query and analyze whether a filter can be pushed below shuffling operators or even down into the storage level itself. Operators like filter aren't black boxes here, since the structure is known and can be reasoned about. The same can be said of column pruning, where the analyzer can figure out through the projections, whether it only needs a subset of the columns for the final output, dropping other unnecessary column data. These and other optimizations can narrow the amount of data that's passed across the wire right from the start. Why keep data around that's just going to be dropped at the end? Save yourself the bandwidth. And the interfaces provided are uniform across all languages, creating a domain-specific language for common tasks. This uniform API means that all languages can be compiled down to the same JVM bytecode, even Python. So, the many scenarios that its Catalyst optimization engine runs through boil down to the same thing for everybody: the ever-decreasing performance hit that Python users incur drops down to nothing. And it's actually quite simple to drop in and out of SQL, as we know that all the Spark libraries extend the core and its RDD abstraction. So you can access the underlying RDD if you find the SQL syntax to be too restrictive, then popping back into SQL when you're ready. There is a caveat though. While working with SQL data frames, you lose compile time type safety, as each row of data is stored in a generic object aptly called row. So, anytime you drop down to an RDD, you'll be given an RDD of type row, and will need to work with the row via its columnar indices, which you can use to convert back to a statically typed object. The newer typed API, introduced more officially in Spark 2.0, brings you much closer to typed SQL. That's covered in the follow-on course, Handling Fast Data with Apache Spark SQL and Streaming, where here we'll focus on the more SQL-esque data frames API to start. In that case, you'll be given the raw rows, which will cause you to lose context like the column names. Although, this is actually when Python shines, as its dynamic nature does allow you to index your row objects' columns by name. So, if an RDD is what you drop down to, then what is the primary abstraction behind Spark SQL? Well, remember the diagram from the introduction module? The block that crossed all the boundaries is that abstraction, blending between data frames and the type dataset just mentioned. It started as schema RDD and wasn't changed to be a data frame until Spark 1.3, when Spark SQL graduated from its alpha phase. It was named schema RDD because all it is, as we've seen, is data grouped into named columns, using column metadata as a schema to back the data. So why change the name to data frames? Because while the underlying data is an RDD, it isn't an RDD. It's just a glorified table. And remember, this new abstraction is a unification across all languages. In fact, it makes Spark SQL more than just SQL. When it was introduced, Databricks stated that this new API makes Spark programs more concise and easier to understand, and at the same time exposes more application semantics to the engine. So, as we'll see in the next section's demo, we can use this abstraction to write SQL or stick to the code, using its Fluent API, which feels a lot like language-integrated queries. But before we head there, some final notes on data frames. I mentioned they're a unification across languages, right? Well, they're actually influenced by data frames in Python Pandas and R. So the name data frames is unified beyond Spark itself. Spark's data frames are more performant, however. That's because Pandas and R's version are built for a single core and use an eager execution model. That means they cannot take advantage of optimizations achieved by lazy evaluation, like pre-filtering the data via predicate pushdowns. But you can easily convert from a Panda or R data frame into a Spark one, also being able to go the other direction from a Spark data frame to Pandas or Rs. Although, since Pandas and R aren't distributed, converting back to this local version is equivalent to calling collect on an RDD, so all the data will need to fit into the driver.